Okay, so hello and welcome back. So in this video we will talk about operations on matrices. And the first operation that we will talk about is basically addition. There is different operations on matrices. So for example, there is addition, there is multiplication, there is basically the multiplication by a scalar, which is a different story. There is also, as far as I can remember, there is a difference of two matrices, and so on and so forth. Now we will start with addition. So now there is an example over here which seems to be a good example. So Fatima has basically two factories at places A and B. So you have basically a factory at place A, and you have a factory at place B, right? Now each factory produces sports shoes for boys and girls. So these factories, they produce sports shoes for boys and girls, for boys and girls. So you have two types of shoes that each of these factories produce in three different price categories. So that they do in three different price categories. Labeled as 1, 2, and 3. So that there is the price category 1, then there is the price category 2, and there is the price category 3. Now, what happens is that the quantities produced by each factory are basically represented as the matrices below. Now, basically, you can say that below we have basically two matrices representing the quantities produced by each factory, meaning that place A and place B. So let me actually erase these, so that, because I don't really need this here. So then basically we have at factory A, and we have factory at A or A, and we have factory at B, and then you have basically the shoes. There are two types of shoes, and meaning that there is shoes for boys, there is shoes for girls, and basically for each of these there is three price categories, meaning that you can write basically, for example, 80, 60, then there is 75, then there is 65, then there is 90, and then there is 85, And so from this you can create a matrix, and this becomes, for example, for boys, this becomes for the quantities created for girls, and this is the price category 1, price category 2, price category 3. And likewise we have 90, 50, 70, 55, 75, and 75. And that becomes your second matrix for factory B. Again, this is for boys, this is for girls, and this is the price category 1, 2, and 3, right? So what that means is that for example, the number of, for example, pairs of shoes produced at factory A for boys in the price category 1 was 80, for girls was 60, for boys in price category 2 was 75, for girls was 65. And the same at factory B was, for example, I don't know, 70, 55, and so on and so forth. Now suppose that Fatima wants to know the total production of sports shoes in each price category. So what Fatima wants to know, the total production of sports shoes, the total production of sports shoes in each price category. Meaning that in price category 1, then the factory is not relevant anymore. Either meaning that at factory A and B, we want to basically in price category, for example, 1 for boys, and in price category 1 for boys again, for example, at factory A, I want to add these together, right? And likewise, I want to add basically the production for the price category 1 for girls to the production for price category 1 for girls at factory B. Add those two together. And then I want to add, for example, 75 and 70 together. And then I need to add 65 and 55 together, because these numbers simply go together. Meaning that, for example, 90 represents the production of sports shoes for boys at factory A in price category 3. And again here, for example, 75 or represents basically the production of sports shoes for boys in the same price category at factory B, for example. But of course, I'm not supposed to add 75 here to 55 here, because they have nothing in common. I mean, logically, I wouldn't want to do that, right? Or I wouldn't want to, for example, add 60 to 75 here, because this is in price category 1 at factory, this is in price category 3 at factory B. And although both of them are for girls, but they are different price categories, so you wouldn't want to add them together unless for whatever reason you wanted actually to do that, for which you would have to find some logical way to do. Otherwise, in this example, what I want to do is that at the end of the day, I want to add the corresponding elements of the two matrices together. So which means that Fatima wants to know the total production of sports shoes in each price category. In each price category. Meaning that in each price category means that of course, boys and girls would be separate, but then the factories would be combined together, of course, right? So then the total production would be basically in category 1, for example. In category 1 we have basically for boys, basically the production at factory A was 80 and at factory B was 90, so I can add 80 and 90 together, right? For basically in category 1, for girls, basically at factory A the production was 60. And at factory B the production was 50, right? Now in category 2, for boys we had basically 75 and 70. And for girls we had 65 and 55. In category 3, what we had basically for boys was 90 and 75. And for girls we had 85 and 75. Now this can be represented in a 3x2 matrix, and these matrices each is actually a 3x2 matrix, of course, as you can see. This is a 3x2 matrix, this is a 3x2 matrix. So this can be represented as a in matrix form as basically you can write, for example, 80 plus 90, then you can write 60 plus 50, then you can write 75 plus 70, then you can write 65 plus 55, then you can write 90 plus 75, and then you can write 85 plus 75, and that becomes a matrix, right? Very simple and very elegant. And basically the good thing about these matrices is that they give you this structure and all of these rules and regulations that they provide you with. For example, then you can use the same concept in order to represent anything, any sort of concept using the same structure. And so for the same reason, matrices are now used, for example, in computer science. They are used in in physics. They are used in all branches of science, because these are, like, for example, you could think of all of these as general purpose tools that you can apply to almost any sort of problem, of course, wherever they are applicable. So now this new matrix, you can call it the sum of the two matrices. This new matrix, you can call it the sum of the two basically former matrices, right? And we observe that the sum of two matrices is a matrix obtained by adding the corresponding elements of the given matrices. Of course, the two matrices that we had were basically these two matrices, if you add the corresponding elements of these two matrices, for example 80 plus 90, 60 plus 50, 75 plus 70, 65 plus 55, 90 plus 75, and 85 plus 75. So these are the corresponding elements of the two matrices. Add them together, you'll get the sum of the two matrices, right? Furthermore, the two matrices have to be of the same order. Of course, if the two matrices are not of the same order, then of course you wouldn't know what to do. You would just simply get confused, because then addition would simply not be possible. Meaning that, for example, suppose that I write 1, 2, 3, and I want to add it to 1, 2, 3, for example, 4, 5, 6, 7, 8, 9. Right? Now the corresponding element, and I want to add them. So the corresponding element of this element in this matrix just simply well, I do not really know definition wise if I can say that, for example, these two would be the corresponding elements in these two matrices. But even if that's the case, then for example 2 could not be added to anything in this matrix, or 3 cannot be added to anything in this matrix, because the corresponding element simply does not exist, right? So if you want to add two matrices together, they have to be of the exact same order, of course. So thus you can say that if A is equal to basically A11, A12, A13, and A21, for example, A22, A23, and is a 2 by 3 matrix, and if you have B as another matrix, as for example B11, B12, and B13, and B21, B22, and B23, right? That is also a 2 by 3 matrix. Then what happens is that then we define A plus B. We define A plus B as a matrix as basically A11 plus B11. And then you have A12 plus B12, corresponding elements. A12 plus B12. Then you have A13 plus B13. B13. Then you have A21 plus B21. Then you have A22 plus B22. Then you have A23 plus B23. And that is the sum of the two matrices. Now, in general, you can say that if basically A is a matrix AI of J, and B is a matrix as B I of J, right, are two matrices of the same order, are two matrices of the same order, say m by n, then the sum of the two matrices, then the sum of the two matrices A and B is defined as as basically as a matrix C, as basically a matrix C of ij of the order m by n, where basically C of ij is equal to A of ij plus B of ij. Right? These are corresponding elements of the two matrices. And that gives the corresponding element in the matrix C for all possible values of I and j. For all possible values of I and j. Right? So as an example, you have, for example, given, this is example number 6. Example number 6, given that A is equal to, for example, a matrix as square root of 3, 1 and negative 1, and 2, 3, and 0, and B is a matrix as, for example, 2 square root of 5, 1, negative 2, 3, and 1/2, right? You want to find A plus B. So, as you can see, they are of the same order. Of course, we have no problem with the orders. So then you can write basically A plus B as basically as a matrix that is in this matrix, each element is the corresponding elements of the two matrices added together. So there you have, for example, 2 plus square root of 3, 1 plus the square root of 5, and then you have negative 1 plus 1 is equal to 0, 2 plus negative 2 is 0, 3 plus 3 is equal to 6, and there you will have 1/2, and that is basically A plus B. Now, we emphasize that as a note, it is to be emphasized that if A and B are not of the same order, then A plus B is not defined. So this is as a note, we can, it has to, this is, they have basically emphasized the fact that if A and B are not of the same order, A plus B is not defined, right? Now, for your own purposes, of course, you can define anything. That's not a problem. But then, provided that what you define does not create contradictions or problems in the rest of whatever it is you're working on. For example, suppose that you go in matrices and you need something in your work which doesn't exist in matrices, for example. Now, you realize that, for example, the whole structure of matrices, you can use it for your work, but then there is something that you need that doesn't exist in matrices. So you can define it, of course, at least for yourself, and use it. There is no problem with that. But then that you can do, provided that whatever it is that you define, that doesn't contradict anything else that there is in matrices. Otherwise, you will have to start your own branch of science, for example. Meaning that you will have to start a whole new concept in mathematics, define your own things and use it for your own, and well, if others, of course, decide to use it, then that's their own choice, that's their own decision. But usually it's not easy to define things in mathematics because, for the simple reason that, for example, it's just not one simple part of mathematics that you're working in, meaning that, for example, when you're working in matrices, you're essentially working in the whole basically areas of mathematics, because they are, whether you like it or not, they are all connected together. Meaning that whatever it is that you define here, you need to make sure that it doesn't create contradiction in algebra, create contradiction in trigonometry, create contradiction in geometry, and so on and so forth. And so far, whatever we have in mathematics, and it's actually a great, it's like a wonder that, I mean, I mean, this whole body of mathematics, as large and as vast as it is, there is no contradiction in it, which is amazing, you know. So yeah, that is basically the whole story. So basically, the whole story is that then if A and B are not of the same order, then A plus B is not defined. So for example, for two matrices, like for example, A is equal to 2, 3, 1, and 0, and B as for example 1, 2, 3, and 1, 0, 1. For these two matrices, A plus B is not defined, because this is a 2 by 2 matrix, this is a 2 by 3 matrix. And then there is another note here. Note number 2 is that we may observe that addition of matrices is an example of binary operation. Is an example of binary operation on the set of matrices of the on the set of matrices of the same order. So hopefully you remember basically the binary operations. We said that basically we defined the binary operation star, for example, as on two sets, basically from, for example, from A to B. And we said that basically this binary operation has to be a function. And I think what they mean by this is that basically the addition of matrices is an example of binary operation on the set of matrices of the same order. Well, right now the binary operations are not I'm not really in that. Well, I cannot really, right now, I cannot think about this, because I'll have to remember everything about the binary operations, and I cannot recollect all of them right But of course, this is an important point, and we will get to that hopefully sometime. I don't know, but right now I cannot basically get my thoughts on binary operations together. It was a large concept that we did, I suppose, in class 12 or 11 or something like that. I don't remember right now. So then that was basically all about the matrix addition. Now another concept that we have, another operation that we have on matrices, is basically the multiplication of a matrix by a scalar. So let's see what that is. Okay, so now basically the multiplication of a matrix, the multiplication of a matrix by a scalar. So let's see what that is. So now the previous example that we had about Fatima running these two factories in branch A and branch B, producing sports shoes for boys and girls in 3 price categories. Now suppose that Fatima has doubled the production at factory A. So now Fatima has doubled the production, the production at factory A, right? In all the 3 categories, of course. In all the 3 categories. In all the 3 categories. So for example, the previous quantities were basically in standard units. In standard units were basically where we had this a matrix for that, and the matrix was 80, 60, for example, 75, 65, 90, and 85. And that was the matrix that was related to factory A, and these were basically the number of, these were the categories for boys, and these were the production for girls. And there you had, for example, price category 1, 2, and 3, right? Now the revised quantities produced by factory A, the revised quantities produced by factory A, are going to be basically, for example, 80 times 2, because you have doubled the production in that factory, or 60 times 2, or you have 75 times 2, or you have 65 times 2, you have 90 times 2, and you have 85 times 2. And that becomes another matrix. That becomes the price category 1, 2, and 3, and that is for boys. That is for boys, and that is for girls. And that is for girls. Now, this can be represented in the matrix form as, in matrix form, this can be represented as, of course, this is already a matrix, but this can be represented as 160, 120, 150, 130, for example, 180, and 170, right? And that becomes the price category 1, 2, 3, and that is boys, and that is girls. Now we observe that the new matrix basically is obtained by multiplying each element of the previous matrix. So each element of the previous matrix is multiplied by 2, and then as a result we get a matrix that has the same number of rows, the same number of columns, only that each element has been doubled, of course, in this case, in this particular case. Now, in general, you can say that basically we may define multiplication of matrix by a scalar as follows. We may define the multiplication of a matrix by a scalar as follows. Now you can say that if A is equal to basically a matrix A of ij of the order m by n is a matrix and K is a scalar, right? Then Ka is another matrix, then Ka is another matrix which is obtained by multiplying each element of A by the scalar K. So then Ka is another matrix which is obtained by multiplying each element of A by the scalar K. In other words, you can say that basically Ka is equal to K times the matrix A, which is Aij m by n, which is the same thing as K times Aij written this way as a matrix of the order m by n. That is basically I comma jth element of K of Ka element of Ka is basically is K times Aij for all possible values, for all possible values of I and j, right? Of I and j. For example, as an example, let's say that, for example, you have a matrix like, for example, 3, 1, 1.5, square root of 5, 7, negative 3, 2, 0, 5. Then 3a, is equal to basically 3 times this matrix, the same matrix, 3, 1, 1.5, square root of 5, 7, negative 3, 2, 0, 5, which is the same thing as, basically 3 times 3 is equal to 27, 3, 4.5, 3 square root of 5, for example, 21, negative 9, 6, 0, and 15, right? And that is basically the multiplication of matrix by a scalar. It's pretty simple concept, but it has many implications and applications. Now, the negative of a matrix, the next concept is the negative of a matrix is denoted by negative a. So you can say that the negative of a matrix is denoted by negative a. We define negative a as is equal to negative 1 times a, meaning that negative 1 taken as a scalar, I'm sorry. As an example, let's say that a is equal to 3, 1, negative 5x. Then negative a is given by basically negative a is equal to negative 1 times a, which is equal to negative 1 times 3, 1, negative 5x, which is equal to negative 3, negative 1, positive 5, and negative x. And also there is the concept of difference of matrices. There is also the concept of difference of matrices. So about the difference of matrices, we have if A is equal to the matrix A of Ij, and B is a matrix as B of Ij, are two matrices of the same order, of the same order. Say, for example, say m by n, then the difference A minus B, then the difference A minus B is defined as a matrix D, is defined as a matrix D equal to basically D of ij, where D of ij is equal to A of ij minus B of ij for all values of I and j. For all values of I and j. In other words, D is equal to A minus B, and these are all matrices, of course. D is equal to A minus B is equal to A plus negative 1 times B, meaning that the negative of matrix B, right? Meaning that instead of subtracting B from A, you add the negative of B to A, right? That is the sum of the matrix A, the sum of the matrix A and the matrix negative B and the matrix negative B. As an example, let's say that you have, for example, you have A is equal to, this is example number 7. Let's say that you have A is equal to this matrix as 1, 2, 1, 2, 3, 2, 3, 1, and B is another matrix of the same order as 3, negative 1, 3, negative 1, 3, and negative 1, 0, 2, right? Then find 2A minus B. You want to find 2A minus B. Now, 2A minus B is equal to, first of all, you need to multiply this scalar 2 pi by A, and then add the negative of B to whatever you get over there. So that is equal to 2 times, for example, the matrix A, which is 1, 2, 3, 2, 3, 1, minus basically the other matrix 3, negative 1, 3, negative 1, 0, 2, and then you can write this as basically multiply this, you will get basically 2, 4, 6, 4, 6, 2, and add this to the negative of this, so you have to take the algebraic opposite of all of the elements, negative 3, positive 1, negative 3, and 1, 0, negative 2, and then add these two together. You will get, adding means adding 2 to negative 3, 4 to 1, 6 to negative 3, 4 to 1, 6 to 0, and 2 to negative 2. So that would be, for example, negative 1, 5, and 3, 5, 5, 6, 0. Right? So that is basically, again, very simple, but I mean, these concepts have a lot of applications in then you will use all of these in determinants, and then you will use all of those concepts in vectors, and then you will use all of those vectors in calculus, and then you will use all of those concepts all together in, for example, in physics, and well, you become a physicist. That's what you do with this. Okay. So that's basically all that we have here. In the next video, we will talk about some of the properties of these matrices. I'll see you in the next video, and thank you.